Hello, welcome to our lesson today on loading of beams and columns for analysis and design. This is part 2 of our lesson on this topic. Once again, my name is Engineer Dr. Egidion Ambrose from the Department of Civil Engineering, Akwa Ibom State University here in Akwa Ibom, Nigeria. So in part 1 of the lesson, we did look at how to transfer load from slabs to beams and from beams to column. We did look at different cases, the one-way span slab, the square slab and rectangular slab. Today we are going to look into exercise so that we can reinforce our understanding in part 1 of the lesson. So this is the question. You have this figure 5. So this is a figure, it is a layout and elevation of a single-story reinforced concrete building. This is the plan, it's a layout. Slab 1, slab 2, slab 3, slab 4, up to slab 9. You have their dimensions and they are grid lines. So you have grid lines A, B, C, D. In this direction, you have grid line 1, 2, 3, 4. So these are the site elevations of the building. So it tells you it's a single-story building. The floor height is first floor height is 5 meter and the second floor height is 3.5 meter. This is the foundation level, the first floor level, and the roof level. So all this give us information on the building. So the question said figure 5 shows the structural layout and elevation of a single story building to be constructed with an in situ reinforced concrete. Now the question is A. Load the following beams for analysis: beam 3A, 3D, beam C1, C4, beam 4A, 4D. B. Determine the axial load and moment carried by column 3C and column 4C at the first floor level. So when we go down, we are going to calculate the moment and the force carried by those columns. Now we have been given this factor. Use the following data. We have thickness of slab 175 mm, total variable action 5 kN per meter squared, load due to finishing and partition 1.5 kN per meter squared, unit weight of concrete 25 kN per meter cube, width of beam 250 mm, depth of beam 450 mm, column section 250 by 250. So with all this information and with this diagram, we can go ahead. The first thing to do is to determine the design load on the building slab. And so to determine the design load, we are going to make use of this information that we were given. So the first thing is, what is the unit weight of concrete? We were told that the unit weight of concrete is 25 kN per meter cube. And what is the thickness of slab? The thickness of slab is 75 mm, which is 0.175 meter. For us to get the self-weight of the slab per strip, the self-weight of the slab is the unit weight of concrete multiplied by the thickness, and that gives us this 4.375 kN per meter square. Now, this self-weight is a permanent action. Which other permanent action were we given? We were given load due to finishing and partition, and we said it was 1.5 kN per meter square. So the total permanent action, that is the GK, is going to be the self-weight of the slab plus the load due to finishing, and that gives us 5.875 kN per meter square. So now we have our GK. The next thing is to find our QK, which is our characteristics variable action. We were told that the total variable action is 5 kN per meter square. So we make use of our GK. QK is 5. So our design load, remember this equation 1 that says N equals to 1.35 GK plus 1.5 QK. And so when we put the 1.35 is the factor of safety for permanent action, 1.5 is the factor of safety for variable action. Once we put that into this equation, we have that our design load is 15.4 kN per meter square. We also need to calculate the self-weight of the beam. So the beam section is 250 mm by 450 mm. We were told width of beam is 250 mm, depth of beam is 450 mm. So what is the unit self weight of the beam? The self weight of the beam is this width times the depth multiplied by the unit weight of concrete. That gives us 2.8 kilonewton per meter. The self weight is given by per linear meter because the length of the beam are not the same. So once we have it in UDL, we are safe. So we go to the actual loading of the beam. This is the plan that is being shown again. We have slab 1, 2, 3 up to slab 9. And so beam 3A3D, this is grid line 3. So beam 3A3D is actually the beam from here to here. The beam from here to here. That is beam 3A3D. And it is supporting load from slab 1, 2, 5, 6, 8, 9. That is the kind of load the slabs it is taking load. It's not carrying load, the whole load from this slab will be part of the load from this slab. So we are going to calculate it load from slab at one at a time. So in span 3A3B, this is span 3A3B, this span of that beam from this place to this place is what we are going to look at. So between those 2 points from here to here, it is taking load from slab 9 and slab 8. How is it taken? Let's look at from slab 9. This is slab 9. Slab 9, if you look at the dimension, is 6 meter by 4 meter. So that means if you divide 6 by 2, that gives you 1.5. That means you're dealing with a two-way spanning slab. And a two-way spanning slab, the trabectory area is usually divided into the short span will carry triangular trabectory area, while the long span beam will carry trapezoidal. And this beam, in this case, it is fall into the short span beam. That is why it is carrying a triangular trabectory area. And this triangle is such that, remember, this place is 45 degrees, this place is 45 degrees. So that means the width here is 4 meter. That means this height itself will also be 4 meter. So from here to here is, from here to here is 2 meter. That is half of the 4 meter. That is why this dimension is shown here. This place is 2 meter. This place is also 2 meter. While this place is also 2 meter. But let's look at it. We are not concerned about this one. We are concerned on this shaded area. And this area, this place to calculate the load of this slab on this beam is this area of the trabectory area multiplied by the design load. So that's what we are doing here. Area is half of a triangle is half base times height. So what is the base? The base here is 4 meter, the height is 2 meter. That's why we have half of 4 times 2 multiplied by this the design load, which is 15.4. That gives us 61.6 kilonewton, which is the load from this slab to this beam. So we go to the other slab, which is this slab from this trabectory area from slab 8, and we do the same calculation. It's a triangle and the area is what? Half base times height. Half. The base is still 4 and the height here is still 2 meter. So we do half base times height multiplied by the designed load, and that gives us again 61.6 kilonewton. So the total slab load is now 61.6 kilonewton plus 61.6 kilonewton. That gives us 123.2 kilonewton. That is the concentrated load. Now to change it to a UDL, you multiply, divide it by the length of the beam. That place, the length here is 4 meter. 4 meter, 2, 2. So we now divide it by 4 and give us 30.8 kilonewton per meter. Now the total load on span is equal to load from slab plus self weight of beam. Remember, we have calculated our self weight of beam to be 2.8 kilonewton per meter. So when we add it with the load of the slab, we have the total load that is on that beam in that span, which is 33.6 kilonewton per meter. And so we go to span 3B, 3C, which is span 3B, this middle span 3B, 3C. So that is what we go. We will consider the load from slab 6 and the load from slab 5. So this is what we do. Load from slab 5. We look at the load from slab 5, which is this one. Slab 5 is a square slab because the dimension is 5 meter by 5 meter. 5 meter by 5. So it's a square slab. And that is why you have the triangular tributary area like this. And this distance from here to here is 2.5 and the base is 5. That's why we say area is half base times height. That is half of 5 multiplied by 2.5 and multiply by 15.4, which is the design load. That gives you 96.25 kilonewton. We go to slab 6. When we go to slab 6, the area, the load from slab 6, this is another triangle, is what? Half base times height. So half here, the base is 5 and the height is also 2.5. So it gives you another 96.25 kilonewton. And so the total slab load is this plus this, and it gives you 192.5 kilonewton. Now the total UDL on the span is this 192 divided by the length, which change it to a UDL, plus the self weight of the beam, which is 2.8, and it all gives you 41.3. So again, we do the same thing in span CD, but know that in span 3C, 3D, 3C, 3D is the same thing like 3A, 3B. So that means the load on this will be the same with the load, and the load here was 33.6. That means the load from this CD 3C 3D is also 33.6 kilonewton. So which is what is written here. Now this is the loading of the beam. Many of you are familiar with this. If you are a civil engineering student, you'll be given this beam, find the bending moment, find the shear forces, and you have never wondered how do they come to this. So this is how they come. So we are drawing the beam again. This is the straight beam. We have span A, B, C, D. And these are the dimension of the span: 4 meter, 5 meter, 4 meter. This is the loading. In this span, we had a load of 33.6 kilonewton per meter. In this span, we had a load of 41.3 kilonewton per meter. And this last one, we have 33.6 kilonewton per meter. And so this is how we can load a beam. If you're doing analysis, once you have a loaded beam, you can go ahead and use any method to analyze this beam to draw the bending moment and the shear force diagram, which you're going to use in your design. Next, we go to the second question, which we were to load beam C1, C4. That is what we are going to do exactly now. So beam C1, C4, that is this horizontal beam. Beam C1, 2, 2, C1, 2, 2, 4, 3, 2, 3, 3, 4. This is this beam, So again, we look at the shaded area are the tributary areas from each of the slab that the beam is carrying load from. So we look at load from slab 1. This is slab 1. The shaded tributary area, slab 1 is a two-way span rectangular slab. It's a rectangular slab, and the beam we are considering is actually a long beam, so it's carrying a trapezoidal tributary area. So if these angles are 45 degrees, you find out that the height of the triangle will always be half of the short span length, that is half of LX. So that is why from here to here is 2, whether it is written or from here to here is 2 meter. From here to here is 2 meter. How do we get this place? By the time you take 2 meter from the 6 meter, what is remaining is 2 meter. That's why we have it here. So the same thing if you come to this one. This is 2 meter. Sorry, this is 4 meter. So that means this height is what? This height is what? half of 4, which is 2 meter. The same thing will be here, 2 meter. The same thing this height, 2 meter. This side will be 2 meter. But this place will be, by the time you take 2 meter here, 2 meter, you take them all from 5. What is remaining is 1 meter. That's why we have this. So that is how we divide this into triangles and trapezium. So load from slab 1. What is the area? This is a trapezium, and area of a trapezium is half the sum of the two parallel side times height. Which are the two parallel sides? This is 6 meter and 2 meter. That's why we have half of 6 plus 2 multiplied by height. This height I say is 2 meter. That gives us the area of this trapezium. By the time you multiply all of them by this design load, it gives you the load carried by the slab. And go to slab 4, which is the same slab 4 here. The area of this trapezium is half of 6 plus 1. This is 6, this place is 1 meter, this place is 6, so this place is 1. We have 6 plus 1, half of it multiplied by the height, which is 2.5. That is from here to here, 2.5. You multiply by the design load and give us this as a UDL. As usual, the total slab load is this plus this, which gives you this. Now, to change it to a UDL, you multiply it by the length. The length of the beam is 6 meter, and you add the self weight of the beam, and everything gives you 45.8 kilonewton per meter. So the next one, you go to span C2, C3, C2, C3. The same thing happens here. Half the trapezoid, half the sum of the two parallel sides. The two parallel sides is 5 meter and 1 meter. So half of that multiplied by the height, which is 2 meter, multiplied by the design load, that gives you this. You do the same thing from slab 5. By the time you calculate from slab 5, you have this and have this value. Total slab load is this plus this, which gives you this 188.65. To change it to a UDL, you divide the 188.65 by the 5 meter, which is the length of the beam, and then add the unit weight of the slab, the self weight of the slab. Everything gives you 40.45. Now, in span C3, C4, which is this span C3, C4, the loading and dimension are same as in C1, C2, the same thing. So this and this are the same. So whatever we had here, which was 45.8 kilonewton per meter, is what we have. So by doing that, you have this load. So we can go ahead and load the beam. This is the span 6 meter, 5 meter, 6 meter. The load here is 45.8, 40.5, 45.8, and so we have that beam, which can now be analyzed using any choice method. So the next one is beam 4A, 4D, which is here. You can notice that this one is an H beam, so in each of the span is carrying load from only one slab, which makes it easier. For span 4A, 4B, load from slab 3 is carrying load from only slab 3, which is this half base times height times a UDL, and it gives us this. And the total load of beam in UDL will be just that one load divided by the 4. 4 is the length of the length of the beam, divided and then add the self weight of the beam, and that gives us this. Span 4BC, 4B4C, which is from here to here, you do the same thing. The load from slab 6, this is how it is calculated. And then the total load on beam in UDL, you divide it by the span, add the self weight of the beam, and that gives us this. Again, in span C3, C4 is the same thing as span CA, CB. So you can take the load that was there. So this is how the beam is loaded. This is the dimension 4 meter, 5 meter, 4 meter. This is the load on this span, load on this span, load on this span. And so by doing that, we have been able to analyze and load the 3 beams. The next thing in the question, what were we asked to do? We were asked to determine the axial load and moment carried by column 3C and column 4C at the first floor level. So that is what we are going to do now. So we are just cutting a part of that column layout that has the column we are looking for. We are looking for axial load on column 3C. Let's go back. This is the main layout. Column 3C, where is grid line 3? This is grid line 3C. So this column is what we are looking at. So we are just drawing out the adjacent, all the slab that has to do with that. So this is where we are drawing out. That is why we are having this. We are drawing out the whole of that place. So this is column C. Column C is carrying load from beam. This beam C, this is beam C 2, 3, beam C 3, 4, beam 3 BC, and beam 3 CD. So you can see in this beam is carrying half of the load, in this beam is carrying half, in this beam is carrying half, and we have analyzed all this beam to find the load that they are carrying. This beam is carrying 40.5. This one is carrying UDL of 33.6. This one is carrying 45.8. This one is carrying 41.3. So the axial load of column 3A is a sum of half the load from these beams that I've just mentioned. So load from beam C3, C4. This is C3, C4. This is this beam. The load from that beam is 45.5 kilonewton meter multiplied by 2.5, because half of this, okay, beam C23, this is the beam, the load is 40.5, which is 40.5. You multiply it by the distance. 2.5 is actually half of the whole beam is 5, but half is 2.5. That's why we have this. So by the time you multiply the UDL by that distance, it gives you an axial load of 101.3 kilonewton. Now load from C3, C4, which is C3, C4, load from this beam is you multiply this 45.8 by this distance. That distance is 3 meter, because the whole span was 6, half of it is 3, so you multiply that by 3 meter, it gives you this. And you also go to this other load from 3 BC. Here you have the load of 41.3, and this distance is 2.5, because the whole beam is 5, so half of it is 2.5. That's why you have this multiplied by 2.5, and it gives you this. Now load from beam C3, 3C3, that is this beam, the same thing, 33.6 multiplied by this distance, which is 2. So you have this. The next thing is to calculate the self-weight of the column. The self-weight of the column is such that we are told that the column dimension is 250 by 250. So this, the width dimension of the column is 250 is now changed to meter, 0.25 multiplied by 0.25. Multiply by the total height of the column. Total height of the column is, remember, the ground floor was 5 meter and the first floor was 3.5. So the total height is 5 plus 2.5, 3.5. So you multiply that, and you multiply everything by the unit weight of concrete, and that gives you a load of 18.3 kilonewton. Note that all these loads are now in kilonewton, and therefore the axial load will be load from all this beam, this beam, this beam, this beam, this beam, plus the self weight of the column. That's what we are doing. This plus this plus this plus this plus this. Which one is this? One is the self weight of the column. So we have an axial load of 422.5 kilonewton. So now we go to calculate the moment on the axis XX. So if we call this the XX axis, now we have the axial load, so we are going to look for the moment. So this is the column. This is the XX axis, this horizontal is the XX axis. This is how we calculate the moment. The x axis is, remember, moment is force times perpendicular distance. So when we come to the x axis now, we have this one which has a bigger load. We have 45.8. 45.8 is the load, the UDL carried by this beam. So we are going to do that UDL multiply by the length of that place, which is 3 meter and is half of the 6. So this 45.8 multiplied by 3, it turns this UDL to a point load. When it turns it to a point load, you now multiply it by the distance which the point load will have, which is half of this distance. This distance was already 3, so half of it is 3.2. That's why we have. So this 45.8 multiplied by 3 turns this to a force, an axial force. We multiply by the distance, which is 3.2. So this is supposed to give us a moment that is going this way. And now the counter moment from the opposite one is going to be, that's why we have minus. The other one is going to be 40.5, which is this UDL, multiplied by the length, which is 2.5 to 2.5. Then that turns into a point load, and you multiply the point load by the distance in which it will act, and that distance is half of this. That's why we have 2.5 over 2. So when you do the whole of this minus the whole of this, you have a force of 75 kilonewton, 79.5 kilonewton meter, a moment. So that is the moment acting on this in this x direction. Now note that moment at the first floor level is usually shared between the two columns meeting there at the ratio of their EI over L. Now let's go back to the section. So this is the section. We were told, let's say, which is column C, column 3C, which is this column, So we are to, it's about here, we are to calculate the moment at this first floor level. So the moment that is acting at this place is the moment is acting both on this column at the first floor level and the column at the ground floor level. So we need to apportion that moment into the portion that is carried by the upper column and the portion that is carried by the lower column. Remember, we are considering what is the one at the lower column. So that is how do we do. We are told that we divide that by the two columns in the ratio of their EI over L. And now if EI is constant, then it will be shared in the ratio of their 1 over L. And in this case, because EI, we are not told anything about EI, that means EI is constant for the two columns. So we are going to share the moment to the two columns in the ratio of their 1 over L. The down column we were considering, remember the length is 5 meters, so you have 1 over that 5 divided by the sum of their 1 over L, which is 1 over 5 plus 1 over 3. By the time you gap that, that will give you a fraction that you will multiply by the moment that was at that point. Once you multiply by this moment, so you now have 32.7 kilonewton meters. That means this is the moment that is acting on the ground floor level that we are considering. So if you follow that pattern in the y direction, y axis, which is this axis, you have the moment here 41.3 acting at the distance of 2.5. You have a moment of 33.6 kilonewton per meter acting at the distance of 2 meters. So this is what you have. This is the 41, the bigger one, 41.3. This is the distance which is this is the distance of the moment, which is half of this distance. Minus, you do the same thing at the other side. When you find out, it is 61.9. And for you to know the moment MYY, the moment at the ground floor level that we are looking for, you multiply it by the ratio of their 1 over L, which is the same thing we did here. And that gives us 25.5 kilonewton meter. And with that, we have come to the end of our exercise 1. The next one, okay, axial load on column 4C. So we are going to can just follow the same pattern, the same thing that we have done on column 3C, you can also do on column 4C. But you know that column 4C in this axis, the vertical axis is carrying load from this beam and this other beam. In the horizontal axis, is carrying beam from only one direction. So this is the solution. You calculate the axial load just the way we did the other one. And then for the moment, you calculate the moment. You will notice that in the xx direction, because the beam is only from one side, we only have this. We don't have minus any other one because there's nothing at the opposite side. So the moment there will be great 206. Now divide it in the ratio of their 1 over I. So that gives you this. You do the same thing in the, remember, if you look at the y direction, we have two beams at the opposite side, so it's always this. That's why you have this minus this, you have this. You now multiply it to that ratio, and with that you have the design axial load and moment in that particular column. So this is exercise 2. You can go ahead and do the exercise 2. You read the question here carefully, and then you go to the, this is the beam, the layout of the structure. You have the slab 1 up to slab 12, and this is the elevation that shows you the floor height. And so with that, you can just come back with this, come back and read this question and do them exactly the way we have done the other one. So with this, I want to tell you thank you for watching the video to the end. And please don't forget to subscribe to this channel so that every time a new video is posted, you will have access to it. Once again, I thank you. My name is Engineer Dr. Edidion Ambrose, and I want to say thank you very much.